I want to thank you guys all for being here. Please chat me if my internet does cut out again. I'm sorry about that. So yeah, today I'm going to talk to you guys about triangulations of non-orientable surfaces. So we're going to kind of break this talk up into three different categories. The first thing we're going to do is introduce our characters, which are going to be some of the spaces that we're interested in talking about. And then we're going to move into mechanics of triangulations. This is like the formulation of the problem that we're interested in. And finally, we're going to go through some constructions and sort of solve the problem that we're interested in. And so I guess to begin, I wanted to start with some of the best advice that I got, both in math and in life, from some of my advisors and mentors throughout my journey in mathematics. And that is that when you get lost, the most important thing is to start with what you know and see where it takes you. So you always want to ground yourself in the things that you're familiar with and sort of use that to leverage things in abstraction, things that you can find out about other things. Yeah. So to begin, we can start with like going off of Rafa's talk about space-time, and even more fundamental question about astronomy. If we go back even further in time, before we had the technology to climb mountains or take pictures from satellites or fly planes, it was really hard to experience the curvature of the Earth. And so if we were to try to naively answer the question about the shape of the Earth, we might just walk outside, maybe go to a place where we could see a lot of Earth, and we'd say, hey, it looks flat. And then if we try to suppose kind of answer this question, we can pose a motivating question as, what are the possibilities? So given that we can walk outside and things look flat, what are the possible shapes of Earth, right? And of course, hopefully not all of us are flat earthers. And at least one of us knows that the Earth is actually a sphere, right? So we can start with the correct answer here. And we know that the sphere is actually like intrinsically round. And it's sort of an unintuitive fact that if you were to zoom in really far into a sphere, things around you are going to look flat. That's kind of a little unintuitive. So we're going to try to first reconcile this fact by developing some technology that'll help us. So to begin, we're going to formalize the sphere as in 3 dimensions as all the vectors whose length is 1. So you can take this norm. You're going to take the components of a vector as the x, the y, and the z, and you're going to square them and then square root the sum of them. And so this is what we're going to call the 2-sphere, or S2. And so how do we reconcile this fact that the sphere kind of has this local property of flatness? So we can invent a tool that we're going to need a lot throughout this presentation called stereographic projection. And because this is super important, I'm going to kind of develop it as an algorithm as opposed to a definition, so that we can kind of gain intuition and hopefully use it later on. So the first thing we're going to do is, my apologies, this should be S2 minus a point because we're going to need to remove a point, my bad. We're going to pick a reference point, right? This is exactly what we want. So the reference point that I'm going to pick is the North Pole, right? And we're going to consider all of the points in the sphere outside of the North Pole. And the next thing we're going to do is we're going to pick emanating rays. So we're going to pick the North Pole and then a ray going through the North Pole, intersecting any other point in the sphere, and then continuing on to infinity. And particularly, we're going to be interested in where this ray intersects the plane. So we're going to take the North Pole, go through the sphere, and finally end up in the plane. And so to kind of put a face to the name, we're going to start with the plane. We have the North Pole up here, and then we have the plane kind of sitting at the equator, right? So this is R2 sitting inside of R3, or all the set of points that have no z coordinate. And so when you develop these rays, right, you see in the North Pole, these are going to intersect the sphere first and then go out to the plane, right? As opposed to on the South Pole, where they're going to intersect the plane and then go to the sphere. And you can kind of see how everything in the South Pole kind of sits inside of this unit disk. And the North Pole kind of is everything outside of the unit disk. And to develop even further intuition, we can actually watch this this movie of this is exactly how this process is going to work for all of the points. So we're going to see it kind of play out. Cool. So we kind of see this unfurling process. So you start at the North Pole and everything sort of flattens out. And we can actually see this. Okay. We can see this on the individual South Pole and North Pole. So this is going to be the unit disk, or everything in R2 that's length less than or equal to 1. You can see it kind of fold up into the South Pole, as opposed to the things that are outside the unit disk. So this picture kind of fits into this one. This is going to be everything that sort of molds into the North Pole. Cool. Cool. So this is going to be stereographic projection, and we're going to use it a little bit. So now we have some intuition. We know what the sphere looks like. Hopefully we believe that we've been living on one for our entire lives. We have a lot of intuition about how spheres work. And now we're going to sort of abstract a little bit to find something that's a little bit more unintuitive or confusing. And the way we're going to do this is we're going to ask the question, what determines a unique point on the sphere? So I'd say that if you were standing at the origin, right, at the core of the Earth, and you were to point out to the surface in any direction, you would determine a unique point in the sphere, right? If I'm standing at the core, I can point out and I'll be pointing to a new place on the sphere. But what if this actually weren't the case? We can abstract by presenting this notion of, what if instead of there being one unique place, it actually determines a copy of two unique places? So there's sort of like a copy of the Earth glued to itself in this way. So this is kind of like a really weird space, and we're going to give it a name so that we can talk about it later. We're going to call this the real projective plane. And this is, if you're familiar with P2 of R, this is a little bit of a peculiar formulation of it as well. So we're going to define this equivalence relation as, we're going to say that points on the sphere are the same if they're antipodes of each other. If you can take a vector and multiply it by -1 to get the other vector, then we're going to say that those 2 points are the same. So we're going to call this we're going to call P2 of R the collection of equivalence classes under this relation. So essentially just take all these equivalent points and then glue them together, and you're going to get this really weird space. And so of course, this is going to be our object that we have zero intuition about. You know, it's hard to even look at a picture of RP2 and really know what you're looking at. So hopefully we're going to try to develop some technology to better understand this by the end of the talk. So we've probably seen triangulations without ever really giving them a name before. If you've ever been to Epcot or seen the Epcot ball, this is actually an example of a triangulation. You have a sphere, you kind of cover it in triangles. This middle picture is a triangulation of a human head, where I guess it's kind of weird, gruesome. But if you have like a fine enough triangulation, if your triangles are small enough, you can kind of get the granular detail of where someone's nose is or where their ears are. And finally, if you Google triangulation, this like cute picture of a dolphin comes up. So we can ask ourselves, what's even the purpose of developing something like this? What can we gain from covering something in triangles? And the answer is, of course, we know a lot about triangles. We know a lot about spheres. We know a lot about triangles. We learned about them in high school. And so we can now use this and leverage this to give us some intuition about P2 of R. It's a really weird space. How can we use these tools of triangles and spheres to help us? And I guess it's a little weird to even think about, like, what does a line or a triangle even mean on a space that you can't really look at? So that's going to be kind of the goal of the remainder of the talk. And so we're going to develop first a meaning to triangulation. And the way we're going to develop these mechanics is we're going to impose some sort of structure on how we build them. So of course, we're going to start with these things called vertices. So these are just points in abstract space, and they can just be anywhere, just points. And we're going to call them a zero simplex or zero simplices, plural. And we're going to develop a notion of connecting 2 points together, which is going to be called a one simplex. So in between, we take all the points in between 2 vertices, and we're going to call that an edge or a one simplex. It's a one-dimensional object. And of course, we can kind of naturally then, wherever space is contained, we can develop these things called triangles, which are going to be called 2 simplices. And you can sort of think of this as the term convex hull, if you're familiar with it, or really just all of the points in the middle of 3 points. So of course, we need to develop some structure, some rules that we want this to follow. And the way we're going to do that is we're going to say that any two simplices need to intersect at a simplex. So of course, simplex then means any number simplex. So for example, if we pick these two simplices, these two triangles, we want to make sure that they intersect at this edge, which we listed in our list of edges. So we're good here. But somewhere where we may run into trouble is where we instead look at this triangle, where this intermediary bold-faced edge wasn't originally in our formulation of what edges we listed. So this triangle isn't in our possibilities of two simplices. So we're not going to allow this. This is going to be impermissible. So now, given this structure, we can kind of build towards a triangulation of P2 of R. And the way we're going to do that, of course, again, is going to be grounding ourselves in things that mean a lot to us, right? So let's start again with the sphere. Oh, my bad. We're going to define a triangulation first. I'm getting ahead of myself. So a triangulation is essentially just one of these geometric simplices, simplicial complexes. So a simplicial complex can just be like a collection of these vertices, edges, faces with that structure. And we're going to say that we have a triangulation of a surface if we can continuously deform that simplicial complex into the surface. So we can sort of move it into it without breaking, tearing, or ripping it. And the goal for the remainder of the talk is going to be, how can we make sense of a triangulation of an abstract space like P2 of R? So if we can do that, hopefully we can gain some intuition about what P2 of R actually looks like. So again, like I said before, we're going to start with the triangulation of the sphere, right? So we're going to take these standard basis vectors. So take one in every coordinate direction, and then -1 in every coordinate direction. And that's going to be these vectors right here. We're going to have, if you're having a little bit of trouble visualizing the 3 dimensions, that you can kind of see that there's a vertex in the middle of every square box. And the next thing we're going to do is we're going to develop our edges to be all of the edges that don't pass through 0. So we're going to make sure that no point is connected to the point directly across the sphere. So this is going to be connected to everything else. You're going to get this sort of like pyramid shape. And finally, we're going to define our two simplices to just be all of the triangles that we just made. This is going to be an octahedron. So now you must be asking, okay, we have a simplicial complex, but how do we continuously deform this into a sphere? Glad you asked. So the first thing we're going to do is, we're going to normalize all of the lengths of all the vectors, and we're going to see this sort of continuous deformation. So you see sort of where it pauses, now everything is sort of sitting on the surface of the sphere. And if you don't believe me, we have this second picture here where the sphere is actually present, and the mesh, these like black lines are the octahedron. You can see it sort of expand into sitting on the sphere. Brilliant. So now where does this get us? The first thing we're going to do is we're going to recall our old friend, stereographic projection. And of course, if you would like to see the video again, I'm really proud of it. Cool, that's stereographic projection. So we're going to use this, and now that we put all of the edges onto the surface, and we put all the vertices and faces on the surface, we're going to sort of unfurl the sphere. And we actually get this, this sort of configuration. So you can kind of reconcile here where everything came from. As you remember, the South Pole kind of folds up to the plane. So the point that was sitting at z equals -1 is going to be moved up continuously to 0. And all of the edges that were connected to it are sort of going to follow with it. So now you can reconcile that these were the 4 triangles that sat on the southern hemisphere of our octahedron. And now the northern triangle has sort of disappeared. And that's because of the nature of this map. We sort of unfurled it. And actually, one of our points disappeared in the process too. In stereographic projection, if you remember, we needed to remove one point, this North Pole. And that sort of was the point that all of these edges are connected to. We can sort of imagine it like somewhere sitting at infinity, like way off the screen. And so now we can kind of see where the other triangles went. This is the bottom edge. These are the other 2 edges. And then these 2 vertices, there's a third vertex sitting out at infinity. Brilliant. So now we've developed sort of a triangulation of the octahedron, and now we can sort of go towards the triangulation that we desire, some sort of better understanding of P2 of R. And the way we're going to do this is we're going to start this whole process again with the icosahedron. So this is an object with, I believe, 30 edges and 12 vertices. It's another Platonic solid, and it has all triangular faces. So if you repeat this whole process, we can do the same normalization of all the vectors. You can imagine that animation where we inflate the icosahedron onto the surface of the sphere, right? And now we remove the North Pole and we stereographically project, and we get these two pictures. Our vertices map down onto these two kind of pentagons, and the edges sort of map into this configuration. Again, we did lose a vertex in the process that's sort of sitting out in infinity, and all of these points intersect it. So this is the sort of idea that we have. And of course, I drew in gray here the unit circle so that we can remember which things are sitting on the South Pole and which things are sitting in on the Southern Hemisphere versus the things that were originally sitting on the Northern Hemisphere. Cool. So now we can go back and remember our definition of P2 of R. So if you remember, P2 of R was simply, we took the sphere and we glued the points on opposite sides to each other. So they're the same point. And we actually, once we recall this, we get a huge stroke of luck. We get really lucky that the way that we picked our vertices here were such that these vertices are actually antipodes of each other. They're on opposite sides, and therefore in P2 of R, they're going to be the same vertices, right? So these are actually going to be our equivalence classes of P2 of R. So the way we picked this originally, we get super lucky, and we're able to then get an explicit method to sort of fold our icosahedron along these like gluing patterns and develop a triangulation of P2 of R. And that's where we get this picture here. This is actually from a course's lecture notes from Johns Hopkins, so thank you. This is an example of a triangulation of P2 of R. And we sort of constructed it by like gluing opposite vertices of the icosahedron. Brilliant. So, okay, we did this. This was a really long process. We developed a lot of tools. What reward did we gain? What was the whole point of this, right? And so to that I say, okay, let's take a little bit of a closer look at this picture. If we highlight these purple edges and sort of simplify the diagram around it, we can make sense of this, this rectangle where opposite vertices are sort of glued together, right? And this is actually a fun activity to take home from this talk, is that if you were to try to maybe cut out a thin strip of paper and glue these two vertices together, you're gonna have to twist the sheet once, or like an odd number of times maybe, in order to create this, this figure. And this is actually something that topologists are very, very familiar with. It's called the Mobius band, or the Mobius strip. And it's a quintessential non-orientable surface. So if you try to build this at home, you can sort of put your finger on it and trace your finger around the entire surface. That is like both sides of it. So there's no sense of sidedness. And so this is actually like a brilliant conclusion that we made just by covering this like weird abstract space in triangles. All we were able to do is start with the sphere, abstract the sphere a little bit, and notice that if we go through some process, we can develop a Mobius strip, and notice that this abstraction actually generated a non-orientable surface. And that's pretty cool. So of course, I encourage you guys to make one at home. And yeah, thank you guys so much. Cool.